So again, when we start calculating, like when we calculated the critical value, that Z star that we calculated, remember, we did in different confidence levels. And to calculate the critical value, what you do is, if I want to calculate 90% critical value, remember that's a right-hand Z score. It's a right-hand Z score. Every Z score belongs to a standard normal curve. So your mean on that curve is always going to be 0, 1. So what you're trying to do is you find the number of standard deviations above or below the mean. That's what a Z score is. The critical value itself is the endpoint, the maximum endpoint that you can have for this particular confidence interval with, right? And so in this particular case, what happens is, if we want 90% confidence, on the inside, you're going to place 90% of your data, right? On the inside, you're going to place 90%. So here you have 90% sitting on the inside. If 90% sits on the inside, how much sits on the outside? Do you remember that? How much sits on the outside?
10%.
10%. We split it up amongst two different sides, right? So that's why you have a 5% here on this side and a 5% over here. If I want to calculate the critical value, then I calculate this 90%. Critical value is always to the left or whatever the right-hand Z-score is. This is the right-hand Z-score that I'm calculating. The critical value is up here, so that's Z star. And so we're going to calculate up to this, which is 90% plus this additional 5%. So I showed you in Excel, if you want to calculate that critical value, we use the function norm.inv, the normal inverse function. And what you do is you type in your probability, and in this case is 0.975, not 0.95, because it's 90% plus the additional 5% that you're calculating right there. Your mean, because it's a Z score, your mean is 0, your standard deviation is 1. When you do that, you get 1.64485. We generally round that up to 1.645. So that's how I got that Z score, the critical value, right? And that's what we talked about last time we did it all by hand. Now, here's what's going to happen that's different then. If you're looking at a 90% confidence interval, this other value that we can calculate is the area on the outside. And you already told me that the area was 10%. That 10% is what we refer to as alpha. It's called the Greek letter alpha. This is the lowercase alpha right here. And we're going to get to this tonight, but the alpha is called the level of significance. So if your confidence level is 90%, your alpha is what's on the outside, that's 10%. And so to use Excel to calculate a confidence interval, Excel says that you need to, let's go find a problem. Let's look at this particular problem right here. Suppose that a sample of n equals 36 cereal boxes has a mean of 362 grams with a known standard deviation of 15 grams. This whole known standard deviation, I told you that matters because we're going to use a Z critical value. Eventually, I think after this test, we're going to talk about T critical values. T critical values might be on this test, I don't know. Generally speaking, in the real world, we don't use the Z critical value because rarely is it that we actually know the standard deviation. Most of the time, we're actually guessing it or estimating from the sample. But in this case, we're going to act like we know it. So because it's a known standard deviation of 15 grams, we're going to use a Z critical value. They want the 99% confidence interval, or find the 95 and the 99%. If I'm at the 95%, right, my alpha is equal to how much area is on the outside if 95 is on the inside?
5.
Anybody want to answer that? 5%. So my alpha here is equal to 0.05. So at 95%, my alpha is 0.05. So when I go back into Excel, because that's what I want to do now, I want to go in Excel and try to calculate this, try to calculate these things. I have not used Excel to actually do this, so this is going to be an experiment for me as well. Using the function CONFI, you have confidence, the first one, and then confidence, you have all these different confidence ones. Confidence norm, confidence T. This is going to be, I think it's confidence norm. Yeah, we're going to use confidence norm for this because it's a Z value. So when I have that, I want confidence norm. I picked the wrong one. 1 second. What is confidence? I guess we can use either confidence. Let's see which one happens. See which one gives what we got earlier. Let's go confidence. So my alpha here is 0.05. Standard deviation was, what was it? Standard deviation was 15. 15. And my sample size was 36. And it gives me this value of 4.8991 or we'll say 4.9. If you come back over here, look at this value right here. It's equal to what? 4.9. It's E. It's the E value that we calculated earlier. So essentially what it does in Excel can calculate the E value for you. And then if we can calculate E, well, the easy part, the next part is just the easy part, because all you have to do is add and subtract the standard deviation. I mean, add and subtract the mean from it. So on any particular problem like this, then if you want to calculate a confidence interval, for instance, if I want the 99% confidence interval, then here's how I calculate that. What's my alpha equal to at 99%?
1.
0.01. So my alpha is equal to 0.01. Well, I could literally go through and calculate the critical value for 99%, then multiply it by the standard deviation and divide by the square root of this. And that's going to give me this E value. But instead of doing all that, I can just go to Excel and calculate E based on Excel from Excel. So when I do that in Excel, all I do is, again, equals CON confidence. Confidence is going to calculate the margin of error. And so my alpha here is 0.01. My standard deviation is still 15. My sample size is 36. Calculate that. First off, let's talk about these two values real quick. This value right here was the 95% confidence interval. This value right here is the 99% confidence interval. What do you notice about the margin of error compared when you compare the two? Which one's larger?
The 99%.
And why is the 99% larger? Let's talk about that. If you are more confident, what should be true about the width of the interval? Should the width of the interval be larger or smaller? Look what confidence does. Confidence wants to try to capture a true value based inside some interval. We become more confident when our interval is wider. So if we're 99% confident, we are more confident. In order to do that, we have to have a wider interval. This value right here, this 6.43957, that value is making the interval wider. All right, that value is making the interval wider. And that's why you're more confident at 99% than you are at 95%. So now that we have that value, then the other thing we need is the mean. And the mean here is equal to 362. So if I want to calculate this, then I can calculate the lower bound. And I can calculate the upper bound for this particular thing by just taking 362 or equals 362. The lower bound would be minus this value right here. That's your lower bound. Your upper bound would be 362 plus this value right here. And that gives me the confidence interval for this. I could have did the same thing for this one as well. And I should have did it for this one as well for y'all to verify that we did it by hand correctly. So the lower and the upper here. The lower would be equal to 362 minus this value. The upper is 362 plus this value. Let me do equals there. Plus this value there. And if you go look and see what we calculated by hand, they got 357.1 to 366.9. We got, when we calculated ours, 357.1 to 366.9. So all Excel is going to do, Excel is going to calculate the margin of error for you. It's literally what it's calculating. And once you have the margin of error, you just need to add, subtract and add the actual mean value. You got that? Does anybody have any questions about that then? Any questions? Y'all okay with all that?
Could
you show me
Yeah.
again the upper and lower right when you did the calculations onto the side?
How did I do them?
Yes, I know you did. I think three
Yeah, so
percent.
look, let me go back to the original problem. The original problem says this. Um, let me try to find a problem that we haven't done yet. Let me go find a problem we haven't done, and we'll do an example. Turn that around the problems. Let me go find another one. Wow. Let's go inside of here. Right here, here, and example. Oh wait. Oh no, wait. These are all docs. Let's try that one. That's hypothesis test. I don't want hypothesis test. My fault. Wrong documents. Yeah. Um, let's go inside here and see what this is. All right, let's do this one. This says a random sample of 100 students selected from a certain school. They are given an IQ test, which has sigma equals 11. The sample mean is found to be 112. Determine the 98% confidence interval for estimating the mean school intelligence. All right. So I'm gonna do it both ways. I'll do it by hand, and I'll also do it with Excel. All right. So when I do it by hand, the first thing I'm gonna need to do is this. I need to identify, remember the formula for any confidence interval is always going to be, for the mean is X bar plus or minus. Because sigma is known, because they give me sigma here, it's going to be Z star times, I need to do the standard deviation, which we call sigma x, divided by the square root of the sample size, which we call n. All right. Now I can identify certain things already. Like for instance, I know that the sample mean is 112. So X bar is equal to 112. Right. I also know that the standard deviation was given to me as sigma is equal to 11. And my sample size n here was given to be 100. So the only thing I really need from this particular problem is going to be my Z star. I need to find Z star. So to find Z star, here's what I do again. Remember, I draw a normal curve. How much is on the inside of this normal curve? Somebody tell me that. How much on the
98.
inside? 98%. So I have 98 on the inside. That means that puts how much on the outside?
2.
2%. How much is gonna, so I'm gonna split that 2% amongst both sides though, right? So how much is sitting on this side?
1.
1%, and over here is also 1%, right? I want to calculate the Z star which sits here. The Z star is up to this value. So I have 98% of the area sitting right here and this little 1% right here. So in Excel, I'm going to go, the Z star is actually equal to, I think it's normal dot inverse, INV. Normal dot inverse. Type in your area, 0.99. Your mean for a Z curve is 0, standard deviation is 1. Where did I get this 0.99 from?
98 plus 1.
Good, 98 plus 1%. That's where I'm getting that from. So when I do this then in Excel, for this 98%, for the 98% confidence interval, right? My Z star, first off, my Z star. Z, where's the star at? Z star is equal to, so start typing in normal so I get norm.inv. Remember, it's 0.99. The mean was 0. Standard deviation is 1. Get that? There's my Z star, 2.32635. 2.32635. So I'll say 2.326. Go to 3 decimals. So my Z star is equal to 2.326. And now I calculate the actual interval itself, right?
And I'm so sorry. What was the 90? How did you get the 99 again?
I added
The 1%
98.
on the other
Yeah,
side?
98 right here plus this 1% over here.
Got it.
Yeah. So when I do this, I do 112 plus or minus my Z star, which is 2.326, times my sigma, which is 11, divided by the square root of my N, which is 100. And all this is just arithmetic. Now you need to clean this up. I like to calculate this value right here first. This value right here is what we call E. That's the margin of error. So to calculate E, you can go to Excel. I'm just using my calculator here. But it's 2.326 times 11 divided by the square root of 100. So my E is equal to 2.55, we'll say 9, 2.559, go to 3 decimals. And this value right here is what we call E. And so now what I do is this, to find the lower bound, I'm just gonna do 112 minus this 2.559. And to find the upper bound, I'm gonna do 112 plus 2.559. So 112 minus 2.559, I get 109.441. That's the lower bound. 112 plus 2.559, 114.559. So there are your lower and upper bounds based off of the by hand calculations, right? Now, if I want to use Excel to do this exact same problem, the only thing different I have to do, the first thing I have to do is I have to identify what the alpha value is, what my alpha is here. So if I'm at 98%, what is alpha equal to?
0.02.
0.02. So my alpha here is 0.02. So if I want to find the margin of error E based off this alpha value, what I do now is I go into Excel. And so the E here, E is equal to, we use the confidence formula. The confidence formula. Alpha is 0.02. The standard deviation from that problem was 11. And the sample size was 100. So I do 0.02, 11, 100. And look what value it gives me for my standard, for my E, which is 2.559 again, right? I'm rounding 3 decimals. And so now if I want the lower bound and the upper bound of this particular interval, all I do is I take my mean. And remember, our mean for this particular problem was this 112 right here. So you're going to take the mean, you're going to subtract the margin of error, and you're going to add the margin of error. So for the lower bound, you're going to do as a formula equals 112 minus the margin of error, which is sitting there. I get this right here. Then I'm also going to do equals 112 plus the margin of error, which is here, right? Which is that right there. If you compare that to what we just got, let's split this screen. There you go. If you compare that to what we just got, here's what we got by hand. Again, make it, there it goes. There you go. 109.441 to 114.559. Which way is quicker? Probably using Excel is much quicker, right? But make sure you know how to calculate an actual like critical value. But the by hand calculation is not bad once you get the critical value, all right? So are there any more questions about confidence intervals? Because that's what we talked about with confidence intervals. Any other questions? Y'all good with that? Thanks for talking to me, guys. I appreciate it.
We're good.
All right, just wanted to make sure. All right, so today we're going to talk about this thing that we call hypothesis testing. All right, bring that out, bring this back. And library. I keep losing my notes. Recovery. Here's what I want. So like I said, I put the new, I didn't like the formatting of the other one, but I mean, they are on Blackboard. They should be the exact same thing. It just should be formatted better. So that's fine too. We're gonna talk about things about how we call hypothesis tests though. And here's the difference. Here's what we did so far. We've just talked about a confidence interval. Did I show you the video for the confidence intervals, by the way? About the Price is Right? Did I show you that video?
Yes, sir.
Yeah.
Okay, cool. So look, in the Price is Right game, the contestant didn't know the actual price of the trip. So she had to try to guess the price of the trip based off something she didn't know. And they gave her a range to try to do that, right? So when we use a confidence interval, we don't know what the actual value is, what the true value is. We're taking a guess at what that value is. In a hypothesis test, there is some claim that has been made about the true value. And we call the true value, by the way, a parameter. I don't know if I told y'all that, but we call the true value so the true value of the population is called a parameter. So we know here in the hypothesis test what the parameter is claimed to be. They have claimed the parameter to be this, right? And we're going to now take some sample data. We're going to take some sample data and see if, based on my sample data, that parameter value is true or not. All right. So that's like me claiming, if I claim, for instance, that the average starting salary for a business major is $70,000 in any field that they work in, something like that, right? But then I go take a sample of 50 business majors, right? And in the sample I take, I get a starting salary, average starting salary of 55,000. What does that make you think about the claim of 70,000? Is it a true or a false claim now? I have an idea.
I mean, it could still be true, but it's skewed. There's someone making a lot
Good job.
more
Good. it could definitely still be true. This could just be one sample that we've taken to 50 people, and we've gotten a whole bunch of people that didn't make close to 70,000, right? What if I did this repeatedly though? Right? What if I did it repeatedly and I kept getting values that were under 70,000? What does it tell you about the claim of, what does that tell you about the claim of 70,000? It's probably not correct. So what happens now is this: we have these sample values. We have this known claim that's being made, and we're going to take a sample. And if the claim that's being made is true, when I take my sample, whatever sample I take, the value that I get from my, and we're going to talk about the mean, the value that I get to the mean should be pretty close to the mean of the population. But if it's not, I want to know, what is the actual probability that if what they're telling me is true, what's the probability? The probability of me making 70,000, if it's true that I should make $70,000 as a starting business major, right? If that's actually true, what is the probability that I find a sample of 50 people who make $55,000 or something even more extreme, which would be something less than $55,000? We're going to be able to do that. And that's called a hypothesis test. So a hypothesis test is basically very similar to a court case. That's how we're going to build this. Because in a court case, here's what happens. When you go to trial, there's a claim being made. Everybody got that? There's a claim being made. And the claim that's being made, essentially, there's actually two claims. The first claim is that the assumed claim. And when you go to court for anything, if you're on trial for anything, what is the initial truth? Anybody tell me what that is?
Innocent until proven guilty.
You are innocent until proven guilty. So the initial claim that we talk about is what we call our null hypothesis. We call it a null hypothesis. In statistics, we write the null as H0 or HO, if you want to call it that. It is the original claim or the assumed to be true claim. So we're assuming that when you go to court, we're assuming that HO is that you are innocent. And we're going to talk about the mean. So let me go and rewrite this. We're going to talk about the population, because basically the innocence is the population. This is the true value. Either you are truly innocent or you are truly guilty. So the parameter here, we're going to talk about the mean. Even though we give means numbers, I'm going to give it this word. I'm going to say the mean is that you are innocent. Here's how we start this. This is called the null hypothesis. You always build this with a hypothesis in mind first. So there's a claim. The claim first off is that you are innocent. That's the first claim. That is the assumed truth. We always assume this to be true. And because you're assuming that to be true, questioning when I go to court, because I'm assumed to be innocent, do I need to show evidence in favor of my innocence? Yes or no?
Yes.
Yes.
You're not
Try it
required
again.
to,
Why not?
No.
because it's
Why
the
don't I have
state.
to show?
It's the
Why don't
state's
I have to?
responsibility to prove their case.
Good. So that's the whole point here. Because the null is assumed to be true, I never have to show evidence in favor that I am innocent, which is why when you hire a lawyer, your lawyer tells you not to talk. Because the only thing you can do is incriminate yourself when you talk. You understand that? You are initially assumed to be innocent. And it becomes the prosecutor's job to actually build evidence against your innocence. So in our particular case, then here's what we have. We have this assumed truth called the null hypothesis, or HO. Right? And then we have this competing claim. We call it the competing claim the alternative hypothesis. And we call it HA. Some people call it HA. Your book or the homework, I think, calls it H1, depending on how many hypotheses you have, H1. H1 competes against this. So if you're not innocent, then what are you going to be?
Guilty.
Guilty. And we write it like this, though. When we write it, we say mu is not equal to innocent. Now, I want you to understand why this matters. Notice that when I wrote this, I'm still using this parameter notation where I use the value mu. Mu is a parameter. It is the true value. It is what is true. And I told you in the original statement that mu is equal to you being innocent. Well, we know that if you're not innocent, then you have to be what? Guilty, right? But notice I did not write guilty right here. What did I write? I
Not
wrote that
innocent.
mu is not equal to innocent. I kept this the same value. The only thing I'm changing is this sign. And so when we get through this, you're going to see, I'm going to write everything where I have a parameter and a number that are both the same values. The only thing that's going to change is going to be this sign here in the middle, right? And this is called the alternative. And this is what we want to show evidence in favor of or against. You want to show evidence in favor of this or against this, but you're not showing evidence in favor of the null. So I need you to understand that when we start this, the null is always assumed to be true. You're always innocent until somebody's able to prove you're guilty. So we're going to start off what we call a two-tail hypothesis test. Right? There's two tails and there's one tail. We'll talk about one tail later. We'll talk about two tail right now, though. We always formulate the null where it involves an equal sign. So when I talk about the null value, I always want to say mu is equal to something. In a two-tail, here's what happens. In a two-tail, I don't know whether the value is higher than what's being stated or lower than what's being stated. But I do know that whatever's being stated, I don't think that's the right value. Right? I don't think that's the right value. For instance, if I say that the average grade in this class is a 3.0, but then I give out grades and some of y'all make less than 3.0, some of y'all make higher than 3.0s, right? So you're wondering, is the average I actually gave you true? Well, you don't know. But what you do know is that you don't think the actual average is 3.0. So this starts out by saying we just think there's a difference. And this is what we call a two-tailed test. And here's how this works. The mean value, the true mean value should sit in a normal curve. Where does the true mean value sit at? Can somebody remind me of that? Where does the true mean sit at in a normal curve? Where does it sit at?
0. Center of the curve.
In the center of the curve. It sits in the center. So here's where mu actually lies. It should sit somewhere in the center, right? And what I'm going to do is I'm going to start taking sample values, X bars in particular. I'm going to start taking sample means X bars. X bar can fall anywhere on this curve, right? If X bar falls in these regions right here, this region right here, it is called our safe region. This is what we call our safe region. And what that really means is that for us, they call it the non-rejection region. What that really means though is safe. That means that X bar is, these X bars that we're getting are plausible for the sample that are plausible for the population that we're looking at. So the sample values we're getting are plausible. But what can happen is X bar can be either too far to the left or too far to the right for us to actually believe it. For instance, if I say the actual mean is 70,000, most values should fall at 70,000. If I get a value of 66,000, maybe it's out here. If I get a value of 75,000, maybe that's out here. But when I start to get values like 55,000, it's still way out here, that makes me start to think that this isn't true. Or if I start to get values like 100,000, which are way out here, that also makes me think that this isn't true. So it's going to fall in what we call a rejection region. And what we're doing is we're rejecting the initial claim. And we're able to reject the initial claim because we have enough evidence to support it, to support the alternative claim. And so when you go to your court case, I want you to think of it in terms of a court case. What is the initial claim in a court case? Somebody remind me, what is it again?
Innocent till proven guilty.
So you are innocent, right? What's the alternative claim?
Guilty.
You are not innocent. You're guilty. Good. You're not innocent, right? If you are innocent, you should fall. If you're truly innocent, when you start looking at the evidence should keep you in this green region. Do you understand that? However, if we start looking at evidence and then we start to see things that don't happen by chance in particular. For instance, if you didn't commit a crime, how likely is it that I would have a videotape of you actually committing the crime? You understand that? Or let's make it even simpler. Let's say that a murder was just committed, right? And in this murder, here's what happened. Here's what we have. We know that it was a female that committed the murder. We know that she was wearing glasses. We know that she also drove a pink Corvette. I got that? Those 3 pieces of information. Does everybody understand that?
Mhm.
So here's what happens in a hypothesis test. Essentially what happens in a court case. The evidence I have is that that the person was a female who committed the murder. How likely is it for me to find any female to commit a murder? Would that make me think that this particular female is the one that did it? Yes or no? Could I automatically reject her innocence based off of that? Probably not, right? Because that's going to be right around, there's a whole lot of females, we don't really have any evidence that's going to support that she committed the murder. If I say she wears glasses, though, what starts to happen? Well, the sample starts to move a little bit. But again, there are a lot of people that wear glasses. I got that? So it's not going to put me out of my plausible thing that she didn't commit the murder. If I say she has a pink Corvette, though, what starts to happen? How many people are there out there with pink Corvettes?
Not very many.
Anybody? There's not very many. So what starts to happen? What do we start to move at? We start to move to what we call our rejection region, which means that what we're looking at is not happening by chance. Something systematically happened to give us this result. In this case, the lady with the pink Corvette probably killed the person, if that's what they saw. So this builds off of, now we have this evidence from our samples. That's basically what we're getting. We're getting evidence from our samples. And if the true mean is 70,000, then most samples should have a value that is close to 70,000. Most means should have a value that's close to 70,000. As a matter of fact, if I pull a mean of, for instance, 68,000, that doesn't really bother me. If I pull a mean of 73,000, that doesn't bother me. What bothers me, though, if I start pulling means of 55,000, or if I start pulling means of 90,000, those start to bother me because they don't align with what it should be. And they move me in and out of a rejection region, all right? So here's what we do. Here's how we formulate a hypothesis. This says, do marketing majors at your school study more, less than, or about the same as marketing majors at other schools? There was a study that was ran and that found the marketing major studied on average of 12.1 hours per week. I'm going to set up a hypothesis test to try to prove that the mean number of hours studied by marketing majors at your school is different from 12.1 hours per week, benchmark reported by the Washington Post. So here's how we start this. The actual parameter here, which we're going to talk about, they're talking about the average, right? And we're actually talking about, when we talk about an average, the parameter here, the parameter for the average is mu. I'm telling you that mu is equal to the true mean number, or the true average, if you want to say it like that, the true mean, the true average, what they want to say, the true mean number of hours that students study. Right? And they tell me now I can set up my hypothesis from that. My hypothesis works like this then. The claim is that, how often do they study?
12.1 hours.
12.1 hours. So what I'm going to claim here, my initial, or the null claim, is that HO is that mu is equal to 12.1. And if we read this based off what we wrote, we already wrote that mu stood for the true mean number of hours that student studies. So this is basically the true mean number of hours that student studies is equal to 12.1 hours. Now, okay with that?
Yes.
Now, what's going to compete against that? Well, they're telling me to test to see if it is what? Telling me to see that at your school it is different. What does different mean? Does that have to be less than 12.1 or greater than 12.1?
Either.
It can be either. It can be either 12.1, it can be greater, or it can be less. We don't really know. We just want to know if it's different. So H1 here, because we don't know the directions, we call it a non-directional test. We say that mu is, and again, look, I'm using the parameter mu because that stands for the true mean number of hours that students study. Mu does not equal 12.1. That means that mu is different than the stated value that's being claimed right now. So every hypothesis test starts with a hypothesis. In this case, we're building a two-tailed test, or a non-directional test. We don't know the direction of the test yet. And so what that essentially means is that when we look at this, right, we're going to test, we're going to say anything that falls on this side, that falls inside of here is safe. Anything that falls inside of there is safe. These are all plausible values. But if it falls out here in these tails, then falls out in these tails, this is our rejection region on this side. This is also a rejection region on this side. So here we're going to reject. So we call it a two-tail. You can fall in either tail and we'll reject it. Now, what happens next is we start to do a little statistics. And the statistics itself is based off of z-scores and critical values. We just got finished talking about critical values. A critical value is a z-score. It is a z-score. And just like when you're in court, here's what happens. We build evidence. And remember that evidence is like the pink Corvette or the lady who wears glasses. A lady who wears glasses is basic evidence. It's not really going to convince you that something is happening different. A pink Corvette, a lady who wears glasses who drives a pink Corvette though, there aren't a whole lot of people that are doing that. So it's going to push you more into a certain direction. Our evidence and statistics is provided by what we call a test statistic. And our test statistic is some form of a standardized score or a z-score. And here's what we know. Because it's a z-score, we know that the mean of every z-curve sits at what number, by the way? Where does the mean of every z-curve sit at? Anybody answer that?
In the middle.
At what number though? It is in the middle, what number?
It's 60.
Try it again. What does the mean sit at? It always sits at what number in a z-curve?
0.
0. It's always at 0. What's the standard deviation equal to? Anybody answer that? What's standard deviation equal to?
0.
Try it again.
1.
1. It's always 1. Standard deviation is 1. So remember on this curve, how many standard deviations are underneath the curve, by the way?
3 on each side.
3 on each side. Good. So we have this. This curve says the mean sits at 0. And the standard deviation is at hold on one second. And the standard deviation is at 1. So I have 0, 1, 2, 3 out here, -1, -2, -3 out here, right? And what happens is this then, generally speaking, I don't know if I told you this or not. I feel like I did though a while back. Maybe you remember me, maybe you don't. When we talk about something being usual and unusual in statistics, a usual value generally happens within 2 standard deviations of the mean. How much area sits within 2 standard deviations of the mean? Can anybody answer that for me? How much area sits between this value and this value? Y'all can answer that.
98.6.
Try it again. How much area is in there?
Is that the 68%?
That is, but it's not 68%. It's how much area? Try it again. 2. 1 is 68%. How much was it in 2? Y'all don't remember? 95%. Good. Thank you. It's 95%. 95% of the area sits within 2 standard deviations of the mean. So generally speaking, when we start to talk about things, usual values normally fall within 2 standard deviations or within 95% of the mean. Right? By the way, what is the critical value or the z-star for 95% of the area within the mean? What is that equal to? Do you remember? Do we know how to calculate that? Do we know how to calculate that? How do we calculate that? What would you do to calculate the 95% critical value?
100 minus 95.
What is that?
Divided by
Good. 100 minus 95 is 0.95. Is 0.05, right? Now what are you going to do? Divide that by what number?
2.
Divide that by 2. You get 2.5. You add it back, and you would do this right here. You would actually calculate the inverse norm. You would do the normal inverse. So if I want to find the critical value for 2, you would do norm.inv 0.97501. When you do that, you get a z star equal to 1.96. 1.96. By the way, it's 1.96. We generally say that anything normal, anything usual falls within 2 standard deviations or 95% of the data. The reason we use the number 2 is because it corresponds to the 95% critical value. 1.96 is really close to 2. So about 95% of the data falls within there. So if it's within 2 standard deviations, it's normally usual. It's normally what we call usual. If it falls more than 2 standard deviations though, more than 2 standard deviations, which is something over here and something over here, this is what we call unusual. So what starts to happen then, when I start to calculate these critical values, we call them we're gonna give them a new name. They're called test statistics. When I start to calculate these new values called test statistics, right? If a test statistic is bigger than 2 or negative 2, it's usually going to be unusual. But that doesn't necessarily mean that, because what we're going to start to do is we're going to compare our test statistic to a critical value. And so we're going to talk about, we already talked about this, the test statistic can then be compared to either a critical value or an alpha level. An alpha value. We already talked about the alpha. The value, the name that we give alpha now, alpha is equal to what we call our level of significance. That's what we call our level of significance. And so if this really corresponds to a confidence interval. The two-tailed test really corresponds to a confidence interval, because what it says is this: if I want 95% on the inside, then I have to have 2.5 here and 2.5 here. So I have an alpha level of 5% on the outside. So my level of significance will be 5%. Alpha will be equal to 0.05. And what we're going to do then is this: we're going to say that if something occurs 95% of the time, then it's usual, which means that if it doesn't occur, it doesn't occur 5% of the time, it's unusual. Anything less than 5% for us is going to be what we consider to be unusual. And when it's unusual, we want to reject it. We don't believe what they're telling us. So every test statistic then, every test statistic has an alpha value associated with it. Every test statistic has an alpha value associated with it. And a test statistic, for instance, 1.96 right here, its alpha value is 0.05. So if z equals 1.96, the alpha value is equal to 0.05. Every test statistic has something like this. Every critical value basically has something like this too, by the way. And so we call that probability that I just told you about, that alpha value, we call it a p-value. We call it a p-value. It's the probability value. And it's the p-value is a probability that's associated with a test statistic. And what it really means is this: the p-value is the probability of getting a test statistic as extreme or something even more extreme if in fact the null hypothesis is true. So if you are really innocent, how likely is it for you to be a woman with glasses that drives a pink Corvette? The first two things are pretty likely, and they will have high probabilities. The pink Corvette, though, is so unlikely to just be somebody different that the chances of being somebody like that is just very unlikely to occur. So what we do then is we look at our sample data, and if I say that the mean value for your starting salary is 70,000, but I grab a sample of 55,000, how likely is that to occur? Well, if most values should be around 70,000, your actual mean value when I grab that set of 50 should be around 57,000 as well. So for me to get a value of 55,000, that's very unlikely to occur. And what it really is telling me is that something's not right. So when we look at our p-value, your p-value can either be very big or it can be very small. The larger the test statistic, the larger the test statistic, the smaller the p-value. And here's why. A test statistic is a z-score. The test statistic is a z-score. And by larger, I can mean it could be larger in terms of positive or in terms of negative. But in a z-curve, the mean is at 0. As you start to move away from 0, I'm looking always at rejecting, I'm always looking at the tails for these particular things, right? So as you move away from 0, what happens to the z-scores? What happens to the z-score on the right? As I move away from 0, as I go this way on the right, what happens to the z-score? Does it get bigger or smaller?
Bigger?
Bigger. So as this gets bigger, what's happening to the area underneath this curve? Is the area getting smaller or bigger?
Smaller.
Smaller. So large z-scores have smaller areas. Likewise, the same thing this way, except it's negative. You get a larger negative number, you get a smaller area. So the larger the test statistic, and whether that means larger negative or larger smaller, the smaller the p-value is going to be, the more unlikely it's going to happen by chance. So let's talk about alpha levels real quick. If I want to find the two critical values associated with each level of significance, here's how this works. If I want to find the 95% confident, 95% level of significance, first off, your alpha here is equal to what? If your inside is 95%, if we have 95% on the inside, what's your alpha equal to? These are off. What is alpha equal for this one?
5%.
0.05. Yeah, 0.05. Now, to find those critical values for that, how do we do that? That's the question, right? I want to find that critical value for 95%. In order to find it, we do it the same way we did the confidence level. How do we do the confidence level? What we have did. If there's 5% on the inside, if there's 5% on the outside, how much is sitting over here?
2.5.
0.025.
2.5. So over here is 2.5%. So what I'm going to do now is I'm going to go to Excel. I'm going to do norm.inv. I'm going to add this 2.5 to this 95, and I'm going to get 0.975. The mean is going to be 0, standard deviation is 1. That means if I want to find this critical value, z star, when I calculate that, we know that this should be 1.96. And if that's 1.96, then the lower one is going to be what? Can anybody tell me that? If the right one is 1.96, how big is this one?
Negative.
Negative 1.96. So what you're literally doing again is you're doing what we already done. We've already calculated critical values. You're still calculating those critical values, right? But you're going to actually write down both bounds this time. So I want to do 90%. 90%, what's my alpha equal to here? What's my alpha equal to here? 10%. 0.1, right? And when I calculate this one, then I'm going to do norm.inv. Well, it's 10%. How much is over here?
5.
5%. So I'm going to do norm inverse 0.9501. This z star, when I do that, norm inverse 0.9501. If you go and calculate it in Excel using norm.inverse, it's equal to 1.645. And so that's 1.645 over there. This is going to be what? Negative 1.645, right? But the thing I want you to understand now is this. I'm giving you this value for the confidence level because you understand that already. In these problems, though, I won't give you the actual confidence level. I'm going to tell you that alpha is equal to 10%. If alpha is equal to 10%, you should automatically associate that with what confidence level?
90.
90%. Is everybody understand that?
Yeah.
And work your way from there to get the z critical value. All right.
To work
So-
it backwards, we've been working it here.
Yes, you're going to work it backwards, basically. Yeah. what I'm doing right now is I'm telling you that normally the problem would say test at the 10% significance level. Well, the 10% significance level really means the 90% confidence level. And because we know how to already do that, I want to build it from there. So 98%, how we calculate this? Well, there's 2%, your alpha is equal to what here? 0.02, right? And again, when you calculate your Z star, that means there's 0.01 sitting out here. So that's norm.inv 0.99, because I'm adding 98 to 1. That's 0.9901. When I calculate that, I get, y'all can go ahead and calculate y'all's in Excel. This Z critical value is 2.326. This Z critical value on the left, negative 2.326. And this last one, 99%, your alpha is equal to 0.01. So that means you have 0.5% over here. So again, norm.inv 0.995 to calculate the Z star here. We do 0.99501. If you go to Excel and calculate yours, I get a Z score equal to 2.576, negative 2.576. So here's what happens then. I want you to notice that as your alpha level starts to decrease, let's start at 10%. When you were at a 10% significance level, right? You had more areas sitting in your tails because you have more area out here, right? As you started to move though, what happens to the amount of area that's sitting in the tails? It gets smaller and smaller and smaller, which really means that you're actually increasing your safe region because you're moving it further and further out. Y'all got that? You're actually increasing your safe region because you're going further and further out. So what we start to do now is, if you start to look at these things that we call p-values, or if you look at your alpha values, right? We're going to make a decision. And alpha is basically going to be this value that says, in a court case, it's the value that says, this cannot happen beyond a reasonable doubt. That's what alpha says. This cannot happen beyond a reasonable doubt, or this can happen beyond reasonable doubt, right? So alpha itself is basically a threshold value. It's a threshold value. And here's what it says. If your alpha value is less than your p-value, sorry, write it the other way around. If your p-value is less than your alpha value, the threshold. Here's the probability of something occurring by chance. Here's the threshold of where we're going to say that it can occur by chance. So if it's less than the p-value, what this really saying is that it couldn't have happened by chance. Something statistically made this happen. When that happens, and what that means is that the woman with the pink Corvette did the murder. The pink Corvette is the thing that pushed us past this, which behaves a really small p-value of something happening by chance. What we do then is we say you're no longer innocent, and we reject the null hypothesis. You're going to reject the null hypothesis. So when the p-value is less than alpha, we always reject the null. If the p-value is greater than alpha, which means that the probability of something extreme happening is pretty large already, then that means it could have happened by chance. we do a process that we call fail to reject. We fail to reject the null. But I want you to understand that we're doing both things with respect to the null. And what I mean by that is when I reject, I don't reject you being guilty. I don't ever reject you being guilty because you being guilty was never in question. It was your innocence that was in question. So I always reject with the assumed truth, with respect to the assumed truth. Or I don't fail to reject your guilt. And when I say fail to reject, here's what this means. If I reject your innocence, what am I saying? What am I really saying? I reject your innocence. What am I telling you?
Guilty.
You're what? That you're guilty. I'm telling you you're guilty. If I fail to reject your innocence, what am I saying?
You're innocent.
You're innocent. You're still innocent. Does everybody understand that? So here, if I reject your innocence, you are guilty. If I fail to reject your innocence, you are still innocent. Now, some people say, why not write this part? Why don't you just accept their innocence? Why can I not accept somebody's innocence?
Because
Am I
even though
telling you
it's to be true, it's not necessarily true.
Good. And what do you mean by that? That's exactly it. I know what you mean by that. So explain it like
Well,
using some other
it's the
terminology. You're right.
But the hypothesis might not be true.
Good. So what we're saying basically is this: even though the evidence says you're not guilty, right? It doesn't mean what? You didn't commit the crime. That just
Correct.
means we don't have enough evidence to support what we put you on trial for. Right? That's
You're
what it's
not
literally saying. That's all.
Innocent, you're just not guilty.
Right. So we're not going to accept your innocence. Another reason we're not going to accept your innocence is because your innocence was never in doubt. You were always assumed to be innocent. So we don't have to accept that at all. But another way we don't accept those is because you can still commit the crime. You just got off. Right? So we don't ever accept this. We don't ever accept HO. We always either reject or fail to reject. And it's all based on the p-value. Just talked about that. All right, so let's look at this. So did I just jump to this? Another way of doing this, by the way, is to look at the actual critical value. All right, we can look at the critical value versus the test statistic. And so what that means is we reject based on the test statistic. But again, you're rejecting when here is your z-score right here. Here's z, here is negative z. You're going to reject if anything falls in these regions right here. That means if you have a test statistic that's bigger than the z-value or bigger than the negative z-value. And we found that by finding our alpha levels. Likewise, you're going to, again, here is z, here is negative z. We're going to fail to reject anything that falls within these values right here. There's two ways we can actually decide to do this. That's because alpha and the critical value are actually related to each other. We've seen that, for instance, at a 5% alpha level, you have a 1.96 critical value. Or at a 10% alpha level, you had a 1.645 critical value. So the way this works is that we can do it like this now. We can reject off what we call our critical values. Here's how this works. This says that the mean is equal to 200. We're testing that against the nulls that the mean is equal to 200. The alternative that the mean does not equal 200. My alpha level here is equal to 0.05. The first question I have is this. If alpha is equal to 0.05, let's relate that to a confidence interval. How big is that confidence interval?
95%.
95%. So if I want to find the critical value for 95%, what do I do? Draw a normal curve. How much area is on the inside? 95%, right? So 5% on the outside. So how much sits on this side right here then?
2.5.
2.5%. We do norm.inv 95 plus 2.5 is 0.975, 0, and 1. My critical value Z star is equal to, we've already calculated this plenty of times, by the way. That's 1.96. This value is, that value on the left is negative 1.96. I'm telling you the Z score. This right here is called the test statistic. This is what I call my test statistic. And it is a Z score. And I'll show you how to calculate that in a few. But right now I'm giving you a test statistic of 1.78. Where does 1.78 fall at? Does it fall in my rejection region or does it fall in my safe region?
Reject.
Look at it again. Here's 0, by the way. Let's put 0 on this so you know where I'm at. That's 0. 1.78. Is it falling in rejection or safe?
Safe.
It's in the safe region. It's in the safe region. It's actually falling inside of here. It's actually falling inside of here right now. This is where that 1.78, because 1.78 falls about right here. Here's that 1.78 value. It's falling in the safe region. Because it falls in the safe region, the question is, do I reject HO or do I fail to reject HO? Do I reject your innocence or do I fail to reject your innocence?
Fail to reject.
You fail to reject your innocence. You fell into the safe region. So I'm going to fail to reject HO or H0 or H0, whatever you want to call it. You fail to reject the null there because you fell into the safe region. Now, look at this next one. What does it mean to fail to reject the null then? What does that actually mean for this particular problem? You fail to reject the null. What does that mean? I fail to reject the null. What does that mean?
It means your hypothesis is correct.
That means that not necessarily your hypothesis is good, because your hypothesis that is what? That the mean does not equal 200. Your actual hypothesis, we're testing because we think that the hypothesis is not 200. Not because we think it is 200. Just like I don't put a person on trial because I think they're innocent. I put a person on trial because I think they're what?
Guilty.
They're guilty. And when I put them on trial, what happened here? The evidence said what?
That you
Right.
couldn't prove that they were guilty.
It's good that you couldn't prove that they were guilty. So what does that mean? That means that if you fail to reject HO, what that really means then, there is a lack of evidence. There's a lack of evidence to support H1. There's a
So
lack
just
of
to-
evidence to support H1.
Just because you reject H1 doesn't mean you have to accept H0.
Right. Right.
Okay.
And we don't ever, but that's the thing, we don't ever reject H1. I'm not going to reject H1. I'm going to fail to reject H0.
H0. I
I'm
said
gonna fail
it
to
back.
reject you. I'm gonna fail to reject your innocence, which means I'm not going to say that you didn't commit the crime. I'm just going to say that there was a lack of evidence to support that you committed the crime. Because you might have committed the crime, but the evidence I have is not enough to actually say that you did. That's the whole goal here. And there's two parts to this. This part right here, this first part, when you fail to reject H0, this is called the decision. The decision is always made with respect to H0. It's always made with respect to the null. This part right here is called the conclusion. In a trial, they read a verdict, right? In a trial, the jurors make a decision. They say, hey, this person is innocent, this person is guilty, right? And then they give you a conclusion at the end of that. Once they say you're innocent, well, you're innocent because there wasn't enough evidence to support guilt. Or they say you're guilty because there is enough evidence to support guilt. But the first part, the conclusion, the decision is always made with respect to H0. The conclusion is always made with respect to H1. So you decide with respect to H0, you conclude with respect to H1. So another example. Here it says that mu is equal to 10 versus mu does not equal 10. Alpha is equal to 0.1, Z is equal to negative 1.78. So again, if alpha equals 0.1, how much area, what kind of confidence interval is that, by the way? What kind of confidence interval is that? 90%. So on the inside of how much then?
90.
90%. Calculate the Z star for that. So we need to do, how much sits on this side then?
5.
5%. So I want to do normal or norm.inv 0.9501. We've already calculated this value too. This Z star is equal to 1.645. This one would be negative 1.645. I got that. I'm now telling your Z value again. Your Z value now is also equal to negative 1.78. So here's 0. Where does negative 1.78 fall at?
It falls to the left.
To the left of negative 1.645. Where does it fall at? It falls in the rejection region. Here's negative 1.78. It's falling in that rejection region. Y'all see that? It's to the left of that critical value, negative 1.645. So it's falling in my rejection region. So here, I'm going to do what? I'm going to make the decision that I'm going to reject what? What do I reject? Do I reject your innocence or do I reject your guilt? Which one do I reject?
Reject HO.
Reject your innocence or reject HO. Why do I reject your innocence? There is enough evidence. This is all evidence-based. There's enough evidence. There's enough evidence to support your guilt. In this case, that's H1. So again, the decision right here, the decision right there, the conclusion right here. Here's the conclusion. But again, all of this is based on evidence. So either the evidence supports or it doesn't support. But it's going to support what you're trying to show. In this case, I want to show H1, or I always want to show H1. That's what I'm testing. But this is what we call making a decision based on the critical value. You can also make a decision, I think, I'll put that in these notes. You can also make a decision based on the p-value. You can also make a decision based on the p-value. Here's how this works. Every test statistic actually has a p-value, associated with it. These first particular examples, I'm going to show you how to do it based off the p-value. I'm going to give you the p-value. Eventually, we get to the point where we can find our own p-values. And so here's what happens now. This says that researchers have postulated that due to differences in diets, Japanese children have a different mean blood cholesterol level than US children. Suppose that the mean level of US children is known to be 170, right? Known to be 170, and it has a p-value equal to 2.231 and alpha value of 0.05. Set up a hypothesis to test whether the mean blood cholesterol level of Japanese children is different than that of US children. So when I write this in H1 or H0, they're claiming that the mean blood cholesterol level is what already? It's known to be what?
170.
So here mu is equal to 170. They tell me that I want to test to see that it is what? Different. So what is H1 going to be? If it's
Not
different, what do I test?
Not
What would
equal
that
to
be?
170.
Mu is not equal to 170. Thank you so much. And here's what else they tell me. They tell me that my alpha value in this particular problem, alpha is equal to 0.05. So alpha is equal to 0.05. And then they give me this value called the p-value. They give me this value called the p-value. And the p-value here is equal to 0.231. Well, remember when we drew this the first time with the normal curve, we know that a 0.05 alpha corresponds to what confidence level?
97.5.
Try it again, that's the actual value. What is confidence level? 95, right? 95. It corresponds to 95% sitting on the inside. And how much is sitting on this side then?
2.5.
How much is on this side? 2.5, right? Everybody understand that? 2.5. What this is telling me then is that in this tail is how much area? How much area sits in this tail? This rejection region is only 2.5% of the area, right? And this rejection region is how much area?
2.5%.
2.5% of the area as well, right? Look at my p-value. My p-value, the probability associated with it is equal to 0.231, right? Well, that's going to be clearly what? That's clearly a lot more than this 2.5 and this 2.5 put together. So because it's a lot more, or because it's more, here's what we say. The p-value, 0.231 is greater than 0.05. And because it's greater than 0.05, it's not going to fall in the rejection region. It's actually going to fall into the safe region. So because it falls into the safe region, we fail to reject the null. We fail to reject the null. When the p-value is bigger than the alpha value, we always fail to reject the null. If the p-value is bigger than the alpha value, we fail to reject. And what that means then, here's the decision. The conclusion says that there is a lack of evidence to support H1. So lack of evidence to support H1. That's why we rejected it. All right. So the p-value is bigger than alpha. We fail to reject. Well, if the p-value, now look at this next one. The diameter of a spindle in a small motor is supposed to be 5 millimeters. The spindle is either too small or too large. The motor will not work properly. The manufacturer measures the diameter in a sample of motors to determine whether the mean diameter has moved away from the target. So again, it's supposed to be 5 millimeters. So HO is that the mean should be equal to 5. H1 is that the mean too little is too small or too large. That means it does not equal 5. My alpha here, alpha equals to 0.01, right? Here's what happens again. We're going to draw a normal curve. 0.01, how much area is on the inside of this normal curve?
99.
99%. So how much is sitting on this side?
0.0.
0.05, we're going to call that, right? Or a point actually is 0.005.
0.005.
Thank you, 0.005. And how much is over here?
0.005.
0.005. That gives me 1% total, right? Look at the p-value here. My p-value is 0.0004. Well, 0.004 is clearly going to be less than this 0.005, right? Y'all see that? So where is it going to fall at? Is it going to fall on the inside or in the rejection regions?
Rejection.
Well, it falls in one of the rejection regions. We don't really know which one, we don't really care, but it's falling in one of the rejection regions. So here we're going to, when the p-value, we're going to say there's 0.004, it's less than your alpha value of 0.01. That's how you read this. And if the p-value is less than the alpha value, when the p-value is less than the alpha value, we reject HO. You reject HO. Why do I reject somebody's innocence? Why do I reject your innocence?
There's
What does the
enough
evidence suggest? Good, there's enough evidence. There's enough evidence to support H1. Right? Enough evidence to support H1. So right now, all we're doing is we're talking about making a decision and coming up with a conclusion, right? And the decisions and conclusions are all based off of the evidence though, all right? So here's an actual example of how we actually run a hypothesis test. This will probably be the last thing I do tonight. So it says the bank manager has developed a new system to reduce the time customers spend waiting for teller services during peak hours. Suppose the manager wishes to use a random sample of 100 waiting times with a sample mean, that's what X bar stands for, is a sample mean of 5.46 minutes and a known population standard deviation of 2.47 minutes. This matters because we're talking about what we call a known population standard deviation. And when sigma is known, we always use a Z critical value. We always use a Z star when sigma is known. So this matters when we use a Z critical value. And they want to support the claim that the mean waiting time under the new system is different than 6 minutes. Is there evidence to support the manager's claim? So what is the assumed or initial truth before we start the test? What's the assumed or initial truth? What is the mean waiting time going to be right now?
5.46.
Try it again, that's a sample. That's what we pulled from the sample. What's the assumed truth though?
6 minutes.
6 minutes is the assumed truth. The 6 minutes, we assume that the mean waiting time is 6 minutes. So we start out by saying that the null mu is equal to 6 minutes. And we want to know if the new one is different than 6 minutes. So what does that tell me? H1 is mu does not equal 6. This value right here is a sample value. That is a sample value. We only put parameters in our hypothesis. The manager thinks that it's different than 6, so that means that it already must be set at what value? If he thinks it's different than 6, then it already must be set at 6, right? So here's how this works now. If I want to find evidence to support the manager's claim, what I need an alpha level. If an alpha level is not given, the general default level is 5%. So we generally set alpha, we generally let alpha equal 0.05 if one is not given. We generally set alpha equal to 0.05. And we know that at 0.05, then, remember, we draw a normal curve. How much area is on the inside at 0.05?
95.
95. And so this is going to be how much over here? 2.5 and 2.5. When we do this, we say the norm dot I and V, right? 0.97501. We already calculated this plenty of times tonight. The C star is equal to 1.96. This one is equal to negative 1.96. So our critical value for rejection is 1.96 and negative 1.96. The next thing we're going to calculate a test statistic. To calculate the test statistic, the test statistic is just a Z-score. How do we calculate a Z-score? Anybody tell me that? You're going to calculate a Z-score? It's been a while. Z is equal to, in case you forgot, which I'm assuming I did.
By the square root of something.
I'll take that. Yes, X bar minus the mean mu divided by
The standard deviation.
yes, the square root, somebody said it earlier, divided by the standard deviation, which is, in this case, sigma over the square root of n. This is how we calculate the test statistic. X bar minus mu over sigma divided by the square root of n. So we come back and look at this. We need to identify a couple of things. We know X bar is that. We know sigma is this right here. Our sample size is n, that's equal to 100. And we can calculate the mean. The mean that we think it is 6. So my test statistic Z is equal to X bar, which is 5.46 minus the mean, which we think is 6, divided by sigma, which is 2.47 over the square root of 100, the sample size. You okay with that?
Yes.
Yes.
So that's the test statistic formula. That's how we calculate it. So let's calculate this now. So I calculate this, I get 5.46 minus 6 divided by 2.47. Divide that by the square root of 100. Here's my test statistic. Negative 2.1, we'll say negative 2.19 or negative 2.186. Let's go 3 decimals. So this is equal to negative 2.186. First off, why is it negative, by the way?
Because it's less than.
It's less than the mean to begin with. It's less than the mean. Do you understand that? It's less than the mean. And we got a test statistic of negative 2.186. Where does that fall at on this curve? Is that going to fall? It's going to be on the left side. Is it to the left of negative 1.96 or is it in the safe region? Where is it falling at?
To the left.
It's falling out here to the left, right? Here's that negative 2.186. Where is it falling at then? It's falling in what region?
The reject.
The rejection region. So what should we do here? We reject HO. Why are we rejecting the null hypothesis? What are we rejecting then? We're rejecting that the mean is equal to 6. Why are we doing that? Is there enough evidence or a lack of evidence here?
Enough.
If I reject your innocence, I'm telling you you're guilty because there's enough evidence. So there is enough evidence. In this case, there's enough evidence to support H1. Well, what is H1? There's enough evidence to support that the mean is different than 6. The mean is different than 6. So this is based off of, right now, this is based off of the critical value, rejecting out the critical value. A simpler way to do this is to reject out the p-value. Because in the p-value, we can skip the step of finding the z-star right here. Because we know our alpha is 0.05. So once I have a z-score of negative 2.186, I want to find the probability of getting some z-score, of finding a z-score that is as extreme or even more extreme than the one I got. Look here, I got a negative 2.186, right? You see that? I got negative 2.186. Getting something as extreme as that would be what? Sitting right here. Or even more extreme would be which way? Left or right? Do I go to the left or do I go to the right? To the left. So what this is really saying is getting a value less than or equal to negative 2.186. We know how to calculate this value, by the way. And we know how to do it because we've done it before, because we're calculating the area on a normal curve, on a standard normal curve. So all you gotta do is do norm.dis in Excel, norm.dis. Where you're calculating negative 2.186. The mean is 0, standard deviation is 1. You're gonna set this to true. You set that to true. So if I go to Excel and I type that in, equals norm.dis. The x value we just calculated was negative 2.186. The mean was 0 because we're on standard normal. Standard deviation is 1. Cumulative, we're going to set to true. Do that. Here's the p-value I get. Now, the problem with this p-value though is, problem with that p-value is the we don't know if it's on the left or the right-hand side. We know from the data it's on the left-hand side, actually. But in all actuality, we really don't know if it's over here or if it's over here. So what I'm telling you then is, when we calculated that, what number do we get? 0.014. That 0.014 probability can either be sitting to this side right here or this side right here. So technically it can be to the left or to the right. We don't know which one it is. And because of that, anytime we do a two-tailed test, whatever we get for one side, we always double it. So we're going to take 0.014 and we're going to multiply it by 2. And that's the actual p-value that I'm looking at for a two-tailed test. So the actual p-value is 0.028. That's because I had to double it. I have to double this. I always double it because I don't know what tail I'm looking at. So it's actually 2 times that probability. It's 2 times this probability to get there, because we look at two tails. And now what happens is this: if my alpha value, if alpha is equal to 0.405, the p-value is 0.028. 0.208 is less than 0.05. 0.028 is less than 0.05. And because it's less than, that means I'm really falling in I'm falling into the rejection region. I'm staying in the rejection region. That's why it's less than. So, group it all. Anyway, what this is really saying then is because the p-value is less than alpha, when the p-value is less than alpha, we also reject HO. We reject HO. And again, we're rejecting because there is enough evidence to support H1. If the p-value is less than alpha, you reject. If the critical value falls into the rejection region, you reject. You have 2 ways to determine what you're going to do, to decide or make a decision. Whichever way you want to use is fine with me. Your homework is going to force you to use both ways. So when you start doing your homework, make sure you know how to do it based off of critical value, like this. Make sure you also know how to do it based off of p-values, like this. P-values mean you calculate a probability in Excel and then come back and compare it to your alpha value. When we're doing two tails, you always double whatever you get in Excel. All right. When you do two tails, you always double what you get in Excel. And a matter of fact, a general rule of thumb for a two tail in Excel is whatever number you get, make it negative, calculate that probability first, and double it. So make it negative, calculate that probability first, and then double it. This one's already negative, so leave it like it is. Calculate that probability. We got 0.014, double it, you get 0.028. It's always 2 times in a two-tailed test. If this would have been a positive here, you would have made it negative, you'd have got 0.014 again, double it, you would have got 0.028. Compared to your p-value, compared to your alpha value, if it's less, you reject. If it's greater than, you fail to reject. Or you can use this method up here. We use critical values. If the critical value falls in a rejection region, you have to actually find the critical value first, your critical values. If it falls greater than the rejection region, if it falls greater than the critical value, it means it's in the rejection region. If it falls within here, it's in the safe region. All right, we'll stop there for tonight, you guys. Anybody any questions?
No, sir.
Thank you.
You.
All right.